Okay, in this short video we're going to be looking at drift velocity. Let's start with what does it mean. So imagine I have a very simple circuit. I've got a cell, I've got a resistor. I have current flowing around my circuit, I. Drift velocity refers to the movement of the electrons in this circuit. So we know that the current represents a flow of charge. We know that that flow of charge in a normal conductor is the charge is carried by electrons that move around the circuit in the opposite direction to current because the electrons are negatively charged. Drift velocity is how we describe that movement of the electrons, and we use the term drift velocity for a good reason. To understand why and to quantify that drift velocity, let's zoom in on a section of this wire. If we do that, I'll just draw a section of this wire here. We could think about the cross-sectional area that it has. I'll label that up. That is A, the cross-sectional area. We have a current in this case. The point I've zoomed in on, the current is flowing to the right, and we will consider an enclosed sort of section of length L. Let's just label that up. That the current is flowing through. Within that section, the things that are carrying the charge, the things that are mobile, are the free electrons. And one of the sort of factors that we need to think about is the density of those free electrons. How many free electrons might we expect to find in this material? So we're going to start by just defining the letter lowercase n as the free electron density. And that is a property of the material that the wire is made from. The free electron density. It is literally just the number of free electrons per cubic meter. Number of free electrons per cubic meter. For a normal metal, for something like copper, that will be a disturbingly high number. I don't actually know the value for copper, but I would expect something like 10 to the 28, possibly even higher, 10 to the 29 free electrons per cubic meter. And hopefully that makes sense. You know, there are a huge number of atoms per cubic meter in a metal. If each atom has lost one of its outer electrons to be shared, to be delocalized in the metallic bonding, then we would expect those sorts of enormous numbers. It's only the free electrons that are able to carry charge around the circuit. So it's only the free electrons that we are interested in here. We don't care about the electrons that are still bound to the ions in the metal. So the free electron density, the reason that's important is that allows us to calculate the total number of free electrons in this enclosed volume that I'm looking at. So let's have a think about that. The volume that I'm considering, consider this volume AL, then the number of free electrons enclosed is simply that volume times that number density. NAL. And that's important because that tells us the total amount of mobile charge in that volume. The mobile charge. Obviously the total volume, the total charge in that volume is zero. There will be as many positive ions as there will be free electrons. But that total mobile charge, that's what carries the current around our circuit. It's the charge that is free to move as represented by these free electrons. So that will just be that number of electrons, NALE, NaL multiplied by the charge on an electron, E. E is the fundamental charge. Arguably, the charge on an electron is minus E. (1.6 times 10 to the minus 19 coulombs). So that tells us the total charge that's able to move in this volume that we are considering. Now let's think about drift velocity itself. In a metal at room temperature, we wouldn't expect these electrons to look the way that I've drawn them at all. They would be moving about at high speeds with a random motion. So at normal room temperature, that random motion would be very rapid indeed. Thermal motion is fast and random. When I say fast, room temperature, we're literally talking about perhaps 10 to the 5 meters per second. Very, very high speeds indeed. However, the motion is utterly random. So if there were no current, if I just had a piece of metal not attached to a circuit, the fact that the motion is random would mean that the average velocity of the electrons is zero, because there would be as many moving left as right, as many moving up as down. That randomness would imply that there is zero average. Mean velocity is zero. Velocity being a vector, of course. So the thermal motion doesn't contribute to what happens in our DC circuit. When I apply a potential difference, as we've talked about in previous videos, the electrons accelerate in between collisions in a given direction. And in this case, they will, of course, be accelerating to the left. Conventional current to the right, transfer of charge to the right, but negatively charged electrons. So these electrons will find themselves all moving to the left. And we define their average velocity as the drift velocity. So the drift velocity, V, is just that overall, that net migration of these electrons to the left. And V is a remarkably small number. It isn't, they move very quickly due to thermal motion, but due to the current, they actually drift quite slowly. And that's why it gets that name, the drift velocity. It's very much a drift, a slow drift of electrons to the left. But bear in mind, the density of electrons is very high. We don't need them to move fast in order to transfer quite a lot of charge, because there are simply so many of them. So, if they're moving with this average velocity V to the left, the time taken for all of the enclosed charge in this region that we're considering, the time taken for it to leave, for it to move past this point in the circuit, will be L divided by V. The time taken for the electrons right at this right-hand edge to get the whole way to over here will just be the distance traveled divided by the speed, divided by the velocity. So the time taken for that enclosed charge to pass a point must be equal to the length of the section we've considered divided by V. Now we've got a total charge that gets transferred, and we've got a time taken. Current is, of course, rate of flow of charge, so we can write current as charge transferred divided by time taken, and we'll find that the length of the section of wire that we consider should cancel out of our consideration, which makes sense. And we get this final expression, nAve. So this allows us to calculate the drift velocity in a material. E is of course fixed. That is the property of electrons. That's never going to change, 1.6 times 10 to the minus 19. N is a property of the material, very large number. A, the cross-sectional area of the conductor. V, the drift velocity of our electrons. And as mentioned, we expect drift velocities to be small. In a normal circuit of the type that I've sort of drawn here, a really simple circuit that I might make in the lab with a cell and a small resistor, if we have something like 0.1 amps flowing through a circuit, drift velocity might be something like 10 to the minus 5 meters per second. So really quite small numbers. When you calculate these in example questions, you might be surprised at just how slowly the electrons actually make their way around the circuit. Okay, that's it. That's drift velocity. That's how we calculate it. Something that is worth noting here, you might recall that filament bulbs operate on the principle of the filament having a very narrow cross-sectional area, and that's the part of the circuit that gets hot. This equation gives us a clue as to why that happens. A smaller cross-sectional area for a given current means a much higher drift velocity for the electrons. That higher drift velocity means more energetic collisions with the ions, more energy being transferred as heat. All right, drift velocity, done.